All right, let's dive in. Today, we're going deep on something that sounds like it's straight out of science fiction, zero-point energy.
Definitely a topic that sparks the imagination.
You sent me a ton of sources, articles, excerpts from physics websites, even some speculation about the future of energy. I have to say, I'm hooked already.
It's a fascinating area for sure.
We've got a lot to cover. I mean, what even is zero-point energy?
ZPE for short.
ZPE for short, right.
We'll dig into the science behind it. And of course, we can't ignore those wild what-if scenarios it opens up.
You know, like a universe where even empty space is brimming with energy. That's the world of ZPE.
Exactly. It's a pretty mind-bending concept.
Yeah.
And luckily, we have our expert here to help us navigate this quantum maze.
Absolutely. So first things first, what exactly is zero-point energy? Let's start there.
Okay, so in the simplest terms, zero-point energy is the lowest possible energy that a quantum mechanical system can have.
Got it.
Now imagine a pendulum swinging back and forth.
Okay, classic pendulum.
Eventually it comes to rest, right?
Yeah.
That's its lowest energy state in classical physics. But in the quantum world, even at absolute zero temperature, where all that classical motion should stop completely, there's still this tiny bit of residual energy. And that's ZPE.
So even when everything seems perfectly still, at the quantum level, there's this underlying hum of energy, like a secret energy source hiding in plain sight.
That's a great way to put it, yeah. And this hum comes from the fact that what we perceive as empty space, well, it isn't truly empty at all.
Right. One of the sources called it a quantum foam.
Exactly. Quantum mechanics shows us that what we call a vacuum is actually this dynamic field, It's buzzing with energy, and these things called virtual particles that are constantly popping in and out of existence.
This is where it starts to get really trippy for me. Tell me more about these virtual particles. How do they contribute to ZPE?
Okay, so picture this. Two particles, one matter, one antimatter, just suddenly appear out of nowhere.
Wha-
They exist for just a tiny, fleeting moment, and then they annihilate each other. And when they do, they release energy back into the vacuum.
Poof.
Exactly.
Yeah.
And this creation and destruction of particle pairs, it's happening all the time, everywhere, and it's all contributing to the energy of the vacuum, which is what we call zero-point energy.
So it's like these virtual particles are tiny sparks of energy constantly igniting and extinguishing themselves within this quantum foam.
I like that analogy.
That's pretty wild.
Now, the reason this all happens boils down to one of the most mind-boggling principles in quantum mechanics, the Heisenberg Uncertainty Principle.
Ah, yes. The Heisenberg Uncertainty Principle. I've heard of it, but honestly, it's always made my head spin a little bit. Can you break it down for us?
I'll try. It basically says there are fundamental limits to what we can know about a particle at any given time. Imagine you're trying to pinpoint the location of a super tiny, super fast marble.
Okay, I'm picturing it.
The more precisely you measure its position, the less certain you are about its momentum, which is basically its speed and direction combined.
So the more we zoom in on one aspect of a particle, the blurrier another aspect becomes.
Yeah. And it's not about limitations in our measurement tools. It's a fundamental property of the quantum world.
So the more we know about one thing, the less we know about another. That does sound pretty uncertain.
Right. And because of this inherent uncertainty, particles can never truly be at rest.
Yeah.
Even in their lowest energy state, there's this constant jitter, this minimum energy level dictated by the uncertainty principle, which contributes to the ZPE.
This jitter idea, does that connect back to one of those sources you sent, the one about a car's location and speed? I think it used that as an example.
Absolutely. The article was trying to explain how you can know either the car's location or its speed with great accuracy, but never both at the same time.
Right. It's like you can't know where it is and how fast it's going at the same time.
Exactly. And that same principle applies to particles at the quantum level.
So you're saying there's this inherent fuzziness to the quantum world.
It's one of the cornerstones of quantum mechanics, yep.
Okay, I think I'm starting to get it, at least a little bit. But how do we know this isn't just theoretical? Is there any real-world evidence that zero-point energy is a real thing?
Great question. And the most convincing evidence comes from something called the Casimir Effect.
The Casimir Effect. Okay, I've heard the name, but fill me in.
It's a real phenomenon. It's been experimentally verified, and it's pretty wild. So picture two metal plates placed really close together in a vacuum.
Okay, in a vacuum. So nothing there but the plates. You'd think they'd just sit there, right?
You'd think so. But what happens is the plates are actually drawn towards each other.
Wait, seriously?
Seriously, it's a tiny force, but it's measurable. And this force, this attraction, comes from those virtual particles we were talking about.
Hold on, so those tiny fleeting particles can actually have a physical effect on something as big as a metal plate.
Yes, the plates basically create a boundary in the quantum vacuum, and that limits the types of virtual particles that can pop in and out of existence between them compared to the space outside the plates.
So there's this imbalance of particles outside versus inside the plates.
Exactly. And that imbalance creates a kind of pressure difference that pushes the plates together.
So it's like proof that this sea of energy we can't see is actually real and can have an effect on the world we can see?
It really is. It's one of the most direct pieces of evidence we have for the existence of zero-point energy and the fact that the quantum vacuum is this dynamic and energetic place.
This is blowing my mind already, and we're just getting started. Now, the big question everyone's probably thinking, can we actually tap into this energy? I mean, the idea of clean, limitless power sourced from empty space itself, that's incredible.
It's definitely a tantalizing possibility, but I'm going to have to play the role of the skeptical scientist here.
I figured you might.
Before we get carried away, there are some massive scientific and engineering challenges to overcome. First off, the energy levels we're talking about at the quantum level, they're incredibly small.
Not exactly like plugging into a wall socket.
More like trying to catch a single raindrop and use that to power your house.
Okay, so it's not really a question of if this energy exists. It's more like, how can we access it in a meaningful way?
You got it. And that how is the real challenge. We'd need to be able to manipulate quantum phenomena, stuff we're just starting to wrap our heads around.
It's a tall order, for sure.
Very tall. One of the sources you sent mentioned a vacuum fluctuation battery.
Yeah, that one caught my eye. Is that a real thing?
It's an interesting idea, more of a thought experiment, really. A physicist named Robert Forward proposed it.
So not something we can buy on Amazon just yet.
Not quite. But it highlights the kind of creative thinking we need to explore when it comes to ZPE. Forward imagined using the Casimir Effect to create a kind of battery, drawing energy from these vacuum fluctuations.
That's pretty ingenious, but for now it's just theoretical.
Yeah, more what if than blueprint, unfortunately.
Yeah. And what about that EM drive thing? I think NASA was looking into that, right?
They were, yeah. The EM drive definitely made headlines.
Something about generating thrust from ZPE.
That was the claim. But the scientific community is, shall we say, skeptical.
I can imagine.
The big issue is that it seems to violate one of the most fundamental laws of physics, the conservation of momentum. You can't get motion in one direction without an equal and opposite reaction.
So no free lunch, even from the quantum vacuum.
Not even from the quantum vacuum, I'm afraid. Plus, there are big problems with how they were measuring the tiny amount of thrust the EM drive was supposed to be producing.
Sounds messy.
It was. But hey, at least they tried something, right?
True. So it seems like the potential of zero-point energy is incredibly exciting,
Yeah.
but we're still in the very early stages of understanding and manipulating it.
That's a good summary.
Well, this deep dive is already taking us to some unexpected places. We've gone from the very basics of zero-point energy to virtual particles to the Casimir effect, and we've even touched on some mind-bending thought experiments. And we're just getting started. Let's take a moment to process all this before we jump back in and explore the implications of zero-point energy and what it might hold for the future.
Sounds like a plan.
All right, welcome back to our exploration of zero-point energy. Before we went down that rabbit hole of virtual particles and the Casimir effect, we were talking about the potential of ZPE to, well, maybe change the world.
The big what ifs.
Exactly, clean energy, space travel, all that good stuff. But as we dig deeper into this topic, I'm realizing there are a lot of different perspectives on ZPE. It's not as simple as just saying, here's this energy, let's use it.
You're hitting the nail on the head. Even though there's a general agreement on the core principles of ZPE, there are different interpretations and approaches to understanding how it all works and what it might mean for how we understand the universe.
So what are some of these different viewpoints? What are we talking about here?
One key difference is in how we view the nature of the quantum vacuum itself. Some physicists see the vacuum as a literal sea of energy, teeming with those virtual particles we discussed earlier.
Right.
And they envision ZPE as this fundamental property of space-time, a vast reservoir of energy just waiting to be tapped.
So it's like there's this invisible ocean of energy all around us, and we just need to figure out how to build a bucket strong enough to hold it.
That's one way to think about it, yeah. But others take a more nuanced view. They argue that focusing just on the energy aspect of ZPE might be a little misleading.
Mm.
They emphasize the importance of the fluctuations themselves, the constant dance of uncertainty at the quantum level, which creates this baseline energy.
So it's not just about the amount of energy, it's about the dynamic, ever-changing nature of the vacuum itself.
You got it. This perspective often uses a framework called stochastic electrodynamics, or SED for short.
Yes, ED, okay.
And instead of focusing on these, virtual particles popping in and out of existence,
Hmm.
SED suggests that a lot of quantum phenomena, including ZPE, can be explained by looking at how charged particles interact with a background of classical electromagnetic radiation, including the zero-point field.
So instead of thinking about those anti-particle pairs appearing and disappearing, we can think about charged particles like electrons constantly being jostled and jiggled by this background radiation.
Precisely. And this constant interaction, this jiggling, could be responsible for many of the effects we attribute to ZPE.
So you have these two main camps, one focused on the energy density of the vacuum, the other on the dynamic fluctuations of the field. Do these different interpretations lead to different experimental predictions? I mean, does it change how we'd actually go about studying this?
That's what's so interesting. In a lot of cases, both frameworks can actually explain the same phenomena, like the Casimir Effect, for example.
Okay, so different paths leading to the same destination.
You could say that. They might offer slightly different explanations of the underlying mechanisms, but the end result, the observable outcome, is the same.
Interesting.
So in the quantum field theory view, the Casimir effect happens because the difference in energy density between the vacuum inside the plates and the vacuum outside, right? The virtual particles outside are pushing harder, basically.
Yeah, we talked about that earlier. Okay, but what about the SED perspective? How does it explain the Casimir effect?
Well, in SED, the focus shifts to how the plates interact with the zero-point field. The plates are constantly absorbing and re-emitting this radiation,
Okay.
but the plates themselves, their physical presence, prevents certain wavelengths of this radiation from existing between them.
Oh, I see. So like a filter, almost.
It's a good analogy.
Yeah.
And that creates an imbalance in radiation pressure, causing the plates to attract each other.
So both interpretations can account for the observed attraction between the plates, but through different mechanisms.
Exactly. And this highlights just how important ongoing research is. By refining our experiments and our theoretical models, we can start to really tease apart these subtle differences in interpretation and hopefully, ultimately, get a more complete picture of what's really happening at the quantum level.
Okay, that makes sense. Now, it seems like the idea of ZPE has been around for a while. Why are we only now really grappling with all of its implications? What's changed?
Well, part of it has to do with the fact that quantum phenomena are incredibly difficult to measure and manipulate. It requires incredibly precise instruments and very carefully designed experiments, but it also has to do with how ZPE was initially perceived. You see, for a long time, a lot of physicists just saw it as a mathematical artifact, a quirk of the equations that didn't have any real-world significance.
An afterthought, almost.
Yeah, sort of. But then, of course, the Casimir effect came along and showed that ZPE is a real thing with measurable consequences.
Right. It went from theory to reality.
And advancements in experimental techniques, particularly in fields like quantum optics and superconducting circuits, have given us more and more sophisticated tools to actually probe the quantum vacuum.
We're getting better at peeking behind the curtain.
We are. And all of this is leading to a resurgence of interest in ZPE and what it could mean, both for science and potentially for technology.
One of those sources mentions something about ZPE and the origin of inertia, and I have to admit, that sounds pretty wild. How are those two things connected?
This gets into the idea of something called Zitterbewegung, which is German for trembling motion. It refers to the rapid oscillations of particles, even when they're at their lowest energy state, because of their constant interaction with the zero-point field.
Okay, so even when a particle seems perfectly still, it's actually vibrating like crazy because it's constantly interacting with the quantum vacuum.
Exactly. And some physicists believe that this trembling, this interaction with the zero-point field, could be the source of inertia.
You're saying that what gives objects mass, their resistance to being moved, could be this constant interaction with the quantum vacuum. That's a pretty radical concept.
It is, and it's still very much a research frontier. But it's an example of how exploring ZPE could lead us to a much deeper understanding of some of the most basic concepts in physics.
It's mind-boggling to think that this sea of energy that we can't even see might be responsible for the very fact that objects have mass and resist being moved. It changes our whole picture of reality.
Right. And this connection between ZPE and inertia has led to even more speculative ideas, like could there be a connection between ZPE and gravity? I mean, if inertia is ultimately an electromagnetic effect coming from the zero-point field, then gravity, which is tied to inertia, might also have its roots in the quantum vacuum.
Okay, now we're really going deep down the rabbit hole.
That's what makes this so exciting. It's a reminder that the universe is still full of mysteries, and the more we learn, the more we realize we don't know.
I love that. Okay, but let's step back from the edge for a minute. We've talked a lot about the theoretical implications of ZPE. What about the practical applications? What are the main challenges that are standing in the way of actually harnessing this energy?
Well, one of the biggest hurdles is simply the sheer scale of the energy involved. The energy density of the quantum vacuum is thought to be enormous, but accessing it and extracting it in a way that we can control, that's a monumental task.
So it's not just about capturing this energy, but about controlling it, directing it towards a purpose.
Absolutely.
Yeah.
It would require a level of precision and control over quantum systems that, honestly, we're just not there yet.
One of the sources mentioned that ZPE might be useful in space travel. Is that something that's being seriously considered?
The idea of using ZPE for space travel, sure, it's a tantalizing thought. Imagine spacecraft powered by the very fabric of space-time itself. We could explore the cosmos without the limitations of conventional fuels.
It does sound like something out of Star Trek, but honestly, is it even remotely feasible? I mean, how would that even work?
It's highly speculative at this point, no doubt. The theoretical challenges are enormous. We'd need to find a way not just to extract energy from the vacuum, but to actually convert it into a directed thrust. And then we'd need to be able to do this on a scale large enough to propel a spacecraft.
Okay, so that's probably a long way off, to put it mildly.
For now, yeah, it's more of a long-term dream than a near-future possibility. But it's the kind of big, audacious goal that drives scientific innovation, right? Who knows what breakthroughs might emerge as we continue to dig into the mysteries of ZPE?
Well, this journey into the realm of ZPE has been pretty wild, to say the least. We've gone from the basics to some truly mind-bending concepts. And as we've seen, it's not just about the energy itself, but about what it means for how we understand the universe, from empty space to the origin of inertia and even gravity. But before we get completely lost in the quantum foam, let's take a step back, reflect on what we've learned, and think about what it all means for the future.
A good place to pause and take stock.
All right, welcome back to our deep dive into the world of zero-point energy. We've explored the science, the different schools of thought, and even dipped our toes into some pretty wild what-if scenarios.
It's been quite a journey.
It really has. Now, as we wrap up this exploration, I want to bring it back to you, the listener. Why does zero-point energy matter? What's the big deal here?
That's the million-dollar question, isn't it?
Right.
Why should we care about this invisible sea of energy and all the, let's face it, kind of bizarre quantum stuff that comes with it?
It's a good question.
Well, I think there are several reasons.
Okay, I'm listening.
For starters, ZPE really forces us to confront the limits of how we usually understand the universe, in our everyday experience. It tells us that even the empty space around us is actually brimming with potential, buzzing with activity at the quantum level.
It's kind of humbling, in a way.
It is. It's a good reminder that reality is far stranger and more amazing than we often give it credit for.
Yeah, it's like suddenly realizing we've been living in a black and white world and someone just turned on the color.
Exactly. ZPE opens our eyes to a whole new spectrum of possibilities. It challenges us to think bigger, to embrace the mysteries of the quantum realm.
And who knows what we might find there.
Exactly. So it's not just about practical applications, it's about expanding our fundamental understanding of the universe itself.
That makes a lot of sense. And it reminds me of something you touched on earlier, that connection between ZPE and inertia. It's a pretty radical concept, the idea that the mass of objects might come from their interaction with the quantum vacuum.
It is, and if you think about it, it's incredibly profound. Because if that's true, it means one of the most basic properties of matter, its resistance to change in motion. It's not an inherent property at all. It's an emergent phenomenon that arises from this interaction with this underlying sea of energy.
So the very solidity of the world around us, it's almost like an illusion created by this constant buzz of quantum activity. It makes you question everything you thought you knew.
It really does.
Yeah.
And this connection between ZPE and inertia, it leads to even more mind-boggling questions about the nature of gravity. If inertia is ultimately an electromagnetic effect coming from the zero-point field, then gravity, which is so closely linked to inertia, it might also have its roots in the quantum vacuum.
Whoa. I mean, that would completely change our understanding of gravity.
Absolutely. And it's a tantalizing possibility that could really revolutionize our understanding of the universe and maybe even lead to new technologies for manipulating gravity itself.
Okay, so we've gone from virtual particles to the possibility of manipulating gravity. It's a long way from just trying to harness ZPE for clean energy.
It is, but that's what's so amazing about science. It's often the unexpected discoveries, the connections we didn't see coming that lead to the biggest breakthroughs. And when it comes to ZPE, we're really just scratching the surface.
It sounds like we're embarking on a journey into the unknown.
In a way, we are.
But we're armed with the tools of science and guided by our curiosity and our desire to understand the universe and how we fit into it.
And who knows what we'll find along the way.
Well, thank you for joining us on this deep dive into the world of zero-point energy. I hope you've enjoyed the exploration as much as we have.
It's been my pleasure.
And as you go about your day, just remember, even in the seemingly empty spaces around you, there's a whole universe of possibilities waiting to be discovered.